It is my immense pleasure to present this topic for third BSc students of our college, Kadirmudin College, Adarampattinam. This topic is very simple topic. Questions are frequently asked in this topic. This slide shows the syllabus related with this topic. That is, this topic is present in Unit 5 of Physical Chemistry 2 paper for third BSc students. 5.1 Raman Spectroscopy, Rayleigh Scattering and Raman Scattering. Stokes line and anti-Stokes lines in Raman spectra, Raman frequency, quantum theory of Raman effect, conditions for a molecule to be Raman active. 5.2 Comparison of Raman and Ion spectra, structural determination from Raman and Ion spectroscopy, rule of mutual exclusion principle. This slide shows a request to viewers. Raman spectroscopy. When an intense beam of monochromatic light is passed through a sample of a liquid or gas, some of the light is scattered by the molecules of the substance. And here monochromatic light means that is a light with a single frequency. And when the light is passed through a sample of liquid or gas, the light is scattered by the molecules. And most of the scattered light has the same frequency as the incident light. This type of scattering without change in frequency in other way, that is energy, that is called Rayleigh scattering. That is otherwise called as elastic scattering. Here the frequency of scatter light is equal to frequency of incident light, that is nu s is equal to nu I. Nu s means that is a symbol for frequency of scatter light, nu I means that is a symbol of frequency of incident light. The scattering which occurs with a change in frequency, that is called Raman scattering, that is inelastic scattering. This phenomenon is called as Raman effect. Here the frequency of incident light is not equal to frequency of scatter light, that is nu s is sometimes less than nu I, or sometimes nu s is greater than nu I. The change in frequency by scattering due to exchange of energy between incident light and scattering molecules. If the photon collides with the molecules in the ground state, it loses energy to molecules, and the scattered light has the lower energy, that is lower frequency, as the incident light, that is nu s is less than nu I. If the photon collides with an excited molecule, that is in the higher vibration level, it gains energy from the molecule, and the scattered light has higher energy, that is higher frequency, as the incident light, that is nu s is greater than nu I. This slide shows schematic diagram of Raman spectrophotometer, and here the incident monochromatic light, that is with the frequency nu I, and this light is passed through the sample. The light is scattered by the molecules of the sample, and the scattered light frequency that is observed by spectrometer, that is spectrum obtained from scattered radiation of a sample, can be observed with the help of spectrometer. That is the variation of nu s is observed by spectrometer. The general pattern of spectrum recorded by scatter light, that is given in this slide, and here the Stokes line. In the case of Stokes lines, nu s is less than nu I, and if nu s is equal to nu 0, then that line is called as Rayleigh lines, and if nu s is greater than nu I, that gives the anti-Stokes lines. Now the difference between frequency of incident light and that of scatter light, that is called Raman frequency, otherwise called as Raman shift, that is delta nu is equal to nu r, that is equal to nu I minus nu s. If delta nu is equal to 0, that gives Rayleigh lines, that is there is no exchange of energy between molecules and incident light, and delta nu, that is positive for Stokes lines, that is scatter line has less frequency than incident light, and delta nu is negative for anti-Stokes lines, that is nu s value is greater than nu I value, and delta nu is negative for anti-Stokes lines, and Stokes lines and anti-Stokes lines are simply called as Raman lines, and the intensity of Stokes lines is greater than anti-Stokes line. Next topic, quantum theory of Raman effect. Now we have two levels, two states. One is ground state, another one is higher energy state, that is virtual state. And if the light, instant light with frequency ni, if it is scattered by, if the light is scattered by the molecules, there is no exchange of energy between light and molecules, then nu s is equal to nu I, that is E dash molecule is equal to E molecule. E dash molecule means that is the energy of the molecule after scattering, and E molecule means that is the energy of the molecule before scattering. Suppose the instant light, it gives energy to the molecule, and the molecule become higher vibration state, and now the scatter radiation has less energy than instant light, that is nu s is less than nu I. This type of scattering gives a Stokes line, and under this condition the E molecule is less than E dash molecule, that is the molecule has higher energy, higher vibration energy state after scattering. And suppose the molecules in the higher vibration state, if it gives energy to instant light, then the scattered light has higher frequency, and the energy of the molecule after scattering is less than the energy of molecule before scattering. This type of scattering gives anti-Stokes lines. So anyhow, nu I plus E molecule, that is equal to nu s plus E dash molecule. If nu I is equal to nu I, nu s is equal to nu I, that is E, then E molecule is equal to E dash molecule. If nu s is less than nu I, then E dash molecule is greater than E molecule. If nu s is greater than nu I, then E dash molecule is less than E molecule. Once again, this slide shows clearly about Rayleigh scattering, Raman scattering, and the Stokes lines and anti-Stokes lines. Rayleigh scattering, that is, in this scattering, no exchange of energy between instant light and the scattering molecules of the sample. That is, nu I is equal to nu s, energy of the molecule before and after passing light of the sample is same. As most of the molecules do not exchange energy, the intensity of Rayleigh line is high. That line, the intensity is maximum comparing with the Stokes lines and the anti-Stokes lines. That is, nu I plus E molecule is equal to nu s plus E dash molecule, as nu I is equal to nu s, E molecule is equal to E dash molecule. Here E dash molecule means the energy of the molecule after passing light, and E molecule means the energy of the molecule before passing light. Next one, Raman scattering. In this scattering, exchange of energy between instant light and scattering molecules of the sample. So nu I is not equal to nu s, energy of the molecule before and after passing light of the sample is not same. That is, nu I is not equal to nu s. That is, energy of instant light is not equal to energy of scatter light. And the Stokes lines and anti-Stokes lines are due to Raman scattering. Stokes lines, that is, this is due to exchange of energy from instant light to scattering molecule of the sample. So nu I is greater than nu s. So as nu I is greater than nu s, E molecule is less than E dash molecule. As most of the molecules reside in the lowest energy state, the intensity of Stokes lines is high in compared with intensity of anti-Stokes lines. Now, anti-Stokes lines means this is due to exchange of energy from scattering molecules with excess of vibration energy to instant light. So, nu I is less than nu s, that is, nu I plus E molecule is equal to nu s plus E dash molecule. As nu I is less than nu s, E molecule is greater than E dash molecule. So the intensity of lines are in the following order. Rayleigh lines intensity is greater than Stokes line, and which is greater than anti-Stokes line. Next one is selection rules for Raman spectroscopy. Now, what is meant by selection rule? Selection rule is the rule which governs the allowed transition. In the case of Raman spectroscopy, there must be a change in polarizability of a molecule during rotation or vibration. Another one is delta J, that is change in rotation quantum number, that is equal to 0 or plus or minus 2. And the change of vibration quantum number delta V is equal to 0, plus or minus 1 or plus or minus 2. These are about selection rules for Raman spectroscopy. Next, another principle, mutual exclusion principle. This principle is very simple, but it is frequently asked in the university examination. So, according to this principle, molecules with the center of symmetry, vibrations which are IR active are Raman inactive, and vice versa. That is, IR active vibrations are Raman inactive, and Raman active vibrations are IR inactive. For example, the case of carbon dioxide, which has center of symmetry, symmetrical stretching vibration is Raman active but IR inactive. But asymmetrical and bending vibrations are Raman inactive but IR active. IR active. None of these vibrations are both Raman and IR active. So in the case of water molecules which has no center of symmetry, all the vibrations are both IR and Raman active. These are about mutual exclusion principle. Well, next topic, differences between Raman and IR spectroscopy. In the case of Raman spectroscopy, any source of light can be used. But in the case of IR spectroscopy, only IR light is used. And in the case of Raman spectroscopy, it is obtained by studying scattered light. But in the case of IR spectroscopy, it is obtained by studying absorbed light. And in the Raman spectroscopy, that arises due to change in polarizability. But in IR spectroscopy, here it arises due to change in dipole moment. And in Raman spectroscopy, water can be used as solvent. But in IR spectroscopy, water cannot be used because water is opaque to IR. And in the case of Raman spectroscopy, it is accurate but not sensitive. But in the case of IR spectroscopy, it is both accurate and sensitive. And in the case of Raman spectroscopy, it can be photographed, but in IR spectroscopy, it cannot be photographed. And in the case of Raman spectroscopy, the molecule with the center of symmetry, symmetric vibration is active, that is due to change in polarizability during symmetric vibration. But in the case of IR spectroscopy, molecule with the center of symmetry, symmetric vibration is IR inactive, that is due to no change in dipole moment during the symmetric vibrations. So these are about differences between Raman spectroscopy and IR spectroscopy. Next topic, applications of Raman spectroscopy. One application, Raman frequency, otherwise Raman shift, that is μr, is a characteristic of the substance and is independent of incident light. So the frequency depends on the nature of the substance, and it is independent. It depends on the substance and it is independent of incident light. So Raman spectroscopy is a tool in characterizing organic and inorganic compounds. On combined study of IR and Raman spectra, one can predict whether a molecule is linear or non-linear, and if it is linear, whether it is symmetric or asymmetric. And another one is the most important application of Raman spectra is to establish the structure of organic molecules. Another one is Raman spectra is useful in studying the strength and nature of forces which are present in the crystal. Another one is it is useful in calculating force constant, moment of inertia of a molecule. With this, I want to conclude my lecture on this topic, Raman spectroscopy. This topic is very simple topic. Questions are frequently asked in the university examinations. Questions like what is meant by Raman effect, what is Raman shift, differentiate Rayleigh scattering and the Raman scattering, differentiate Stokes line and anti-Stokes lines, or compare the intensity of Rayleigh lines, Stokes lines, anti-Stokes lines, and write the selection rule for Raman spectroscopy. What is meant by mutual exclusion principle, and illustrate the application of Raman spectroscopy. These are some of the questions frequently asked in the university examination. I wish all the students all success. I expect the valuable comments from the viewers, the comment box. I thank one and all. Thank you.